All right, so today we're going to be talking about the limit of a function. And before we get started on the notes sheet, I just wanted to remind you a little bit about what we had done last year with limits at the very beginning of the year. So we also talked about it again when we were talking about our vertical and horizontal asymptotes. So if I have some kind of graph that continues, that is a continuous graph, then I can talk about what happens, for example, as x goes out towards negative infinity, as x approaches negative infinity. Do y'all remember that? As x approaches negative infinity or goes out to the left, then we can say that y approaches something. And the y values are getting closer and closer to this line, which that line is the x-axis, so y is approaching 0. Now on the other end of this graph, as x goes out to the positive infinity direction, so as x moves to the right, then y is also getting very large. Sorry, that was supposed to be an x. Y is also getting very large and going towards infinity as well. So we did some things similar to that when we were talking about our asymptotes, because we said if this happens, then we have a horizontal asymptote. But those are the only limits that we really did. But the limits that we're going to talk about today are not necessarily at the ends of a function. We were just talking about end behavior when we did this last year. Now, one other thing that I do want to point out before we do this worksheet is this. If I have a graph, and let's just say, let me put a few points on here. Now, let's just say it's a line. And this line has a gap in it right there. Well, I know that at 0, 0, I've got a value. I know that over here at 2, 2, I've got a value. And I know I have values that run all the way up to that hole. And so I could say I have a value of this function at at 0.9999999 and get really close. Or I could, say I have a value on the other side of that hole and get really, really close. But I can't actually get to the value here at 1. And that's what we're going to be talking about today. Now, the value of our function, for example, f of 2 here is 2. That is our output. The f of 0 is 0. That is our output. So the value of the function is not the same as the limit of a function. So we're going to try to stress that today as well. So let's go ahead and take a look at our worksheet here. It says up here that the limit of f of x as x approaches c is the number the function values are approaching. And this is our key word here, approaching. It does not mean that it has to actually equal that value. Here is our notation. So let me talk a little bit about that. This is read as the limit as x approaches c, which is usually some constant value, of f of x. The limit as x approaches c of f of x. So it says here that they want us to use these graphs to figure out if the function has a value and then the number that appears to be the limit as x approaches c. Now, some of these may not have a limit that exists, so it says the limit may not exist. So let's take a look at this first one. We're going to do the function value first. So the value of this function at 1. So if I go to where x is 1, it looks like the output here is 2. Okay? This notation for the limit says, well, the limit as x approaches 1 of this function is what? Well, as I approach 1, as x approaches 1, as I get really close, I have an output value really close to 2. If I come in from the other side, and get close to 1. The output is very, very close to 2. So the limit as x approaches 1 coming from either side is still going to be 2. Okay, so one other thing I want to make clear is that the limit coming from the left and the limit coming in from the right, they have to be approaching the same value in order for the limit to exist. So let's write that down. As x approaches c from the left and right, f of x must approach the same value. And you'll see what that means here in a minute if that's not something that's clear to you right now. Okay, so let's look at this next one. There we go, a little bit better. Okay, so on this next one, let's talk about the value. The value of the function at 1, the output value here is 1, 2, 3. So 3. As x approaches 1, so if I come in really close to 1, the output is going to be close to 3. If I come in from this side, I'm still close to 3. So my limit is also 3. All right, so let's take a look at the next one. This one, our output value at 1. If I go to 1, the output here doesn't exist. I'm going to say D and E. It's empty set. There is no output value at 1 that exists. Now, the limit, on the other hand, if I get really close to 1 and come up here, I have a value that's close to 2. If I come in from this side and I go up by there, the output value is close to 2. So the output here is getting close to 2 as x approaches 1. That is my limit. So this would be an instance where the value and the limit are not the same. Okay, so let's go ahead and look at the next one. For this one, looks like I have an I want to find the output at 1, and I have an output value. It's where the circle is closed in. So the output value is -1. Okay, so as I come in towards the limit as x approaches 1 from the right, from this side, and I go to where the output is, it would be up here somewhere. And if I come in from this side, that value would be down here somewhere. So as I said up here a minute ago, when I approach from the left and the right, the output has to approach the same thing or the limit does not exist. So although it's approaching a value here and here, they're not the same, so the limit does not exist. All right, let's take a look at the next one. Our output value at -2. So if I go to -2, open circle, the output value does not exist. But the limit at -2, okay, so if I come in from the left towards -2, it looks like I'm going up here really close to +2. If I come in from the right-hand side, also approaching +2. So the limit from the left and the right are the same. My limit is +2. One more of these. For this one, they're wanting the output value at -2. Although they didn't draw it in, we assume that this is closed circle here. So because I didn't put an open circle. So the output at -2 is -2. The limit at -2, if I come in from the left towards -2, the output is up here at +2. If I come in from the right towards -2, the output is -2. They are not approaching the same thing, so therefore the limit does not exist. All right, so the front of the page was talking about limits and whether they existed when we were looking at a graph, and that makes it a little easier. But if I am asked about the limits as x approaches some value for a function that's given the equation instead of the graph, then the importance of knowing what that graph looks like is increased. It's kind of what I was talking about when we were reviewing the other day. If I know what this graph looks like, then I probably could get a really good idea pretty quickly of what's happening. So let's talk about this graph real quick before we fill in our chart. We should know that this graph is shifted to the right too, because remember the denominator is kind of like having that parentheses, and inside the parentheses it does the opposite of what you think. So this graph is going to be shifted to the right too. So this is just the parent function graph shifted to the right. So this is asking me about the limit as x approaches 2. Well, as x approaches 2, this is where 2 is, coming from the left it goes down towards -infinity, coming from the right it goes towards +infinity, so probably this limit does not exist. Those are not approaching the same thing. But let's take a look at the chart for this function as well. So if we put this equation into the calculator, so here it is, and then we're going to go to our table. Okay, I'm going to set this on ask, and we'll go to the table. All right, that way I can just input these values. So let's fill this in pretty quickly. Here we got 1.9, 1.99, 1.999, 1.9999. All right, so we can see what those values are doing. So let's fill those in. -10, -100, -1,000, -10,000. All right, and then we're going to do the rest of these values. So 2.00, whoops, didn't type in 2. 2.0001, 2.001, 2.01, and 2.1. So looks like we're going back the other way. Oh, somehow one got left out there. All right, so we've got 10,000, 1,000. This one was 100, and then 10. So when I look at this chart, in order to interpret what's happening in the graph, we know that we're looking at what x is doing as we approach 2, and we're approaching 2 right here in the center of the graph, because we're coming in towards 2 from the left and from the right. And then I look at what's happening to y. Well, coming in from the left, y is going towards -infinity. Coming in from the right, y is approaching infinity. That is not the same thing. The limit does not exist. All right, for the next one, I'm going to go ahead and do the chart first and see if we can figure it out from the chart, and then we'll talk about the graph. So we have x squared minus 4 over x minus 2. All right, so here's our equation. start again. Okay, so we've got 1.9, 1.99, 1.999, 1.9999. So 3.9, 3.99, 3.999, 3.9999. All right, coming from the other way, 2.0001, 2.001, 2.01. So we got 4.0001, 4.001, 4.01, and 2.1, 4.1. All right. So as I look at this chart, it says the limit as x approaches 2, and so we're approaching 2 right here, coming in from the left and from the right. And if I look at the left and right y values, these look like they are getting close to 4. It looks like this limit is going to be 4. Well, if I were going to graph this one so that I could determine from the graph, the first thing I would do is factor, and then I would see that this thing actually reduces. And so it turns out that this takes on the characteristics of the line x plus 2. It just happens to have a hole in it, right? There's a hole at x equals 2. So that's why my limit can't actually come right here. You can't actually put 2 in the equation, because if I put 2 in the equation, it makes the denominator 0. But this graph is really just the graph of the line x plus 2 but when I get to 2, there's just a little gap. All right, which leads us to the next thing. If there weren't a gap, if I could put 2 into the equation, would that work? And the answer is yes, because if I put the 2 in the equation and it's something that I can actually evaluate, then that means that the limit and the value are the same, kind of like they would be in this problem. The limit and the value would be the same, like the first example or the second example. The limit and the value are equal. So that leads us to our next problem here. We already know this is a line. A line doesn't have any gaps in it, doesn't have any asymptotes. So I know that the output, or the value, and the limit would have to be the same. So for this kind of problem, you can just plug it in. 2 times 1 plus 1, so I get 3. And the output is 3. And you can graph the line, and you can see that the output and the limit are both 3 when x is approaching 1. All right, for this next one, we also could plug in the 3. Now, if we wanted to evaluate just the function at 3, we would use this equation, because this is where x is equal to 3. So let's plug that in. It would have 2 times 3 minus 4, or 6 minus 4, which is 2. We would not, if we were just looking for the value, we would just say the value is 2. We would not use this equation. But if I want to find out if they actually are approaching the same thing from the left and the right, I do need to put in the 3. So I do 5 minus 3 is also 2. So it looks like this limit is going to equal 2. Now, if I were to graph these equations, let's take a look at that. We know that 3 is what we're concerned about. And this is the equation of a line with a slope of 2 going through -4. So So I would start down here and go up 2 and over 1, up 2, over 1, up 2, over 1, up 2, over 1. And that's where I need to start drawing that line, because everything to the left of this is defined by this equation. This is called a piecewise function. So a piece of the function looks like this line, and the other piece looks like this line. So this line starts at 5 and has a slope of -1. So down 1, right 1, down 1, right 1, down 1, right 1. So that's what the graph would look like. And so now that we have a picture of the graph, we could visually see that as x approaches 3 coming from this side, we have 2. As x approaches 3 coming from this side, we have 2. So the overall value, the overall limit is 2. The value is also 2. There's no gap and no asymptote in that function. So the limit and value are the same. All right, one more. This one only gives us the graph, the chart. So no graph. We can't actually, we could plot the points, but we don't really have the graph of this function. But we know that we're looking for the limit as x approaches 0. And in my chart, 0 would be right in here. So approaching 0, coming from the left and the right. If I look at the y values, this is approaching, looks like positive 1.1 coming from this way, approaching negative 1.1, and those are not the same. So this value, we don't know if the value exists because they didn't ask us about 0. They didn't give us that in the chart, but we know that this limit as x approaches 0 does not exist. They are not approaching the same thing.